In this video, I want to show you how to set up a simulation in Comsol that uses kinetic expressions from Yu and Semprini, a paper of theirs in 2004, to describe the sequential degradation of PCE to TCE, DCE, vinyl chloride, and ethylene. The equations are here, and this is an example of sequential degradation. And I explained how to set this up in an earlier video, but what I want to do with this video is update that previous video and show you how to set up the analysis to avoid a problem of overshoot that happens with the previous setup. So here's the Comsol model. It uses the transport and dilute solution physics. So we'll go ahead and put the physics in. This model is already set up, so we don't have to go through the setup, but I'll show you just how you would go about setting it up if you were starting from scratch. So transport of dilute species physics, put it in, and then here's the setup that has already been done. I'm just going to delete that, and I'll show you the setup. I'm just use a simple 2D geometry. The concentration will be uniform everywhere. We have these 5 different dependent variables, concentrations of the 5 different species, and we set the diffusion constant equal to 1 times 10 to the minus 9 meters squared per second for all of them. And the initial conditions is a concentration of 1,000 of PCE. And then these are the reactions. These are the names of the reactions. And here are the reactions defined. There's a bunch of constants that are in the paper that I put in a file and imported. And then here are the reaction kinetic expressions. There are 4 expressions for decay, and then there are 5 expressions shown here, and these are the kinetic expressions that I showed you under the reaction node in the physics. So the decay expressions use a function called monad. This uses monad kinetics, and there's the equation and the arguments that are used. This is the standard monad equation with inhibition terms. I also defined a step function that I'm going to use as one of the ways to help avoid overshoot. So there's the monadic function that I just showed you that's being called, and there are the parameters that get passed in. You can see the 1 plus CPC, those are the inhibition terms. So let's try running this. Here's the concentration with time, and you can see the concentration that we start with decay to 0, but now this is DCE, and it's going negative in a big way. So that's impossible. We can't have a negative concentration. And the reason it does that is because the decay expression here does not turn off when the concentration goes to 0. So what I'm going to do is modify this expression with another set of expressions here. And this one, in this example, I use the same monad function, but I multiply it by that step function that I showed you. That step function goes from 0, steps up to 1 at a value that's just slightly greater than 1. So as the concentration decreases and approaches 0, this will require that the decay term goes to 0. And you can see that we don't have that negative DCE, and the VC, the vinyl chloride, decays, and ethylene goes to the initial concentration of the PCE, 1,000. So that's the expected result. It takes 1 minute and 51 seconds using that step function. And this is another way to do it with a Boolean instead of a step function. So you can see there, right there, it's C PVC is greater than or equal to 0. That's a Boolean expression. And if that's true, then we do the function as shown. If it's false, if the concentration goes negative, then it sets it to 0. Everything else is the same. And we'll go ahead and try this. So the behavior is pretty much the same. We have some quick decay at the beginning, and then here's the VC going to 0 and the ethylene going to 1000. So that's pretty good. Notice that one went 1 minute and 31 seconds. So in this case, the Boolean expression is a bit faster than the step function. This is the step function. I want to show it to you again. It's stepping up from 0 to 0.1 on the x-axis. It steps up to 1. So that's the way you avoid that overshoot. You can do it two ways. In this example, it looks like the Boolean expression works. Well, they both work. The Boolean expression is a little bit faster than the step function.